Hello everyone. In this video, we are going to derive the solution to the problem of a single degrees of freedom damped forced vibratory system. So to begin with, let me draw the spring mass system, of course, with a force that is acting on it. So you have a spring, and you can see that there is a mass. Okay, that's our mass M. And it is resting on a spring, and there is a damper. That's right. And I'm going to represent the force that is acting. So maybe there is a force that is acting on this particular system, and that force may vary in a sinusoidal manner like this: F sine omega t. Well, F is the amplitude, and you can see that the amplitude of the force is going to vary in a sinusoidal manner. So if I just plot the graph, you will be getting a graph something like this. That's right. If you plot a graph by taking the force value along the y-axis and the time along the x-axis, right? How does the force vary with respect to time? Of course, the force is going to vary in a sinusoidal fashion with respect to time. You may ask me this question: what is the type of force that actually varies in a sinusoidal manner? I can give an example to this. Say, for example, this particular system, there is an eccentric mass. Okay, I can represent that by white color. You can see that there is an eccentric rotating mass in this particular mission. Say that the magnitude of the eccentric rotating mass is m. Then what is going to happen is, as this mass is rotating, it exerts a centrifugal force that acts radially outwards. So that can be represented by this LO. Of course, the magnitude of the centrifugal force is m into omega square into r. And of course, this is going to be theta, the angle theta. If you resolve this force into two components, maybe you look for blue color. I'm resolving the force into two components. One is along the x direction and another one is along the y direction. And what is the magnitude of the force along the y direction? Maybe you can call this force as F, which is m into omega squared into r. The magnitude of the force along the y direction is F into sine omega t. Exactly that, right? The magnitude of the force along the y direction, it is F, which is m into omega squared into r, into sine theta. Okay, maybe I can just do one more step to clarify this. Actually, you will say that the magnitude of the force along the y direction, it is m into omega square into r into sine theta. That's right. Well, I'm calling this m into omega squared into r as F. That's right. And I'm calling this theta as omega t. And that's an easy explanation. You know, velocity is distance by time. So angular velocity omega is angular distance divided by time. So theta, which is a function of time, is simply omega into t. So that's how I can write theta as omega into t. Now, this is clearly a system where you have a mission where the rotating mass is eccentric. It's not exactly at the center. It is slightly offset to the center. So what's going to happen is, as it spins, it exerts a centrifugal force that acts radially outwards. A centrifugal force at any instant of time can be resolved into two components. The y component, if you just localize your attention on the y component, it exerts a sinusoidal fashion force as represented here. And that is going to make the mass jump up and down like that. So this is the action force, F sine omega t. So I'm going to write the action and what are the various types of reactions that will be produced in the system. So the action is F sine omega t. So that I can write that here, F sine omega t. That's the action. And what are the various reactions that is going to happen? See, first of all, there is a mass that is jumping up and down. According to Newton's second law, you give a push to the mass, then the mass is going to offer a reaction that is equal to ma. So it is m into d square x by dt squared. So Displacement is x, velocity is dx by dt, acceleration is d squared x by dt squared. So that is one of the reactions. Is there any other reaction? Yes, the damper is going to offer a reaction, that is c into dx over dt. You know what is damping coefficient, right? It's the ratio of the damping force to the velocity. So you work out for damping force, it is damping coefficient into velocity of the mass. And there is, of course, you can see by Hooke's law, the spring is going to offer a reaction. It is k into x. Remember, this is a suspension system. Out of these three forces that are offering the reaction, the spring force and the damping force will be transmitted to the foundation. Well, this is a bit of information that you want to keep at the back of your mind. This will be very useful when you do vibration isolation problems. Okay, this is the governing differential equation. So let me put a box to this. And I'm going to derive the solution to this governing differential equation. Now, every differential equation has a secret that is hidden, and that secret is this x. So when you solve this governing differential equation, you will be able to find this secret x of t, how the displacement of the mass varies with respect to time. Well, this displacement of the mass varies. How does it vary with respect to time is given by two components. The first one is the complementary function, and the second one is particular integral. Now, I really don't want to use the words complementary function and particular integral because it is not very, very intuitive. So instead, I want to use the words. For this particular physical scenario, the solution x of t, you see, I think this time it's going to make some sense. That is the solution by free vibration, solution for free vibration, so free vibration plus the solution to the forced vibration plus the solution to the forced vibration, solution for forced vibration. So for forced vibration. So instead of using the notations, instead of using the words complementary function and particular integral, I am using the words free vibration solution plus forced vibration solution. Is that okay? So maybe this is playing the role of complementary function. Here we go. And this is playing the role of particular integral. That's right. Now you may ask me this question, well, we have a forced vibration system, clearly. So why do you want to add the solution to the free vibration, add the solution of free vibration to the solution for forced vibration? This is one of the questions that you may be asking. Well, when you find the solution, it's going to be a general solution. It should be a general solution. And when you're trying to aim at a general solution, suppose in the given situation, the force is going to be 0, at least your solution, the general solution, should reduce to free vibration system solution. Hope that is clear. So if the force is going to be 0, automatically the F term, the capital F term in the solution is going to be 0. Obviously, your solution will be reduced only to complementary function. The second question that you will be asking, well, adding the free vibration solution to the forced vibration system, don't you think that it will affect the response of the system? Well, it's not going to affect the response of the system because this solution is actually, to some extent, it will have an exponentially decaying term, right? Lambda e raised to the power minus lambda t. Since it has an exponentially decaying term, as time progresses, this term, the complementary function, will become 0 as time progresses. So it will have an effect to the solution at the beginning, but as time progresses, the solution will become 0. Right, the complementary function is going to become 0 because of the exponentially decreasing term. In a very short duration of time, it's actually going to become 0. Hope that is clear. So now let us try to find the particular integral, because the solution, complementary function solution, that is the solution to the free vibration, is already derived. You can check it through. Maybe I can give the description. I can give the link in the description. You can check it through at your leisure. Okay, now let us find the particular integral solution. So x of t, which is the solution to the particular integral, which is very simple. So obviously, let us make a guess. Let us make a guess. See, the mass is jumping up and down, right? So the displacement of the mass should also vary in a sinusoidal manner, right? The displacement x should also vary in a sinusoidal manner. So you will be tempted to assume a solution like, say for example, one constant b1. I'm not using a1 because the constant a1 is already used for the solution to the free vibration. So I will use b1 instead. b1 sine omega t. So you will be tempted to assume a solution like this, or you will be tempted to assume a solution like b2 cos omega t. Well, both are going to be trigonometric, both are trigonometric functions, right? Fine. Now, the question here is, if you solve by assuming one of these functions, then again you are going to get a solution to the, you are going to end up with a problem where c becomes 0, which means the damping coefficient becomes 0. So you will be ending up with a problem where the damper doesn't exist. Of course, we have a damper. So you cannot just assume a solution like b1 sine omega t alone, and you cannot assume a solution like b2 cos omega t alone, because if you're assuming the solution b1 sine omega t, or if you're assuming the solution b2 cos omega t, and then you try to solve the problem, you will be getting c value as 0 in one of the steps. I tried this. You can check it through. I tried this. Well, we have a damper. C is not 0. So what do? You assume a solution where you add the both. b1 sine omega t plus b2 cos omega t. Now you try to solve the problem. Now the damping coefficient is not equal to 0. That means that we can permit the use of damper. Of course, our system has a damper. All right. Now let us try to find dx by dt for this particular case. So what is dx by dt? It is omega. If you differentiate sine, it becomes cos b1 into cos omega t. If you differentiate omega t, you are going to get omega. I have taken that omega outside. And if you differentiate cos, you are going to get minus b2. Cos omega t is sine omega t. Of course, if you differentiate omega t with respect to time, you are going to get omega common outside. So you take it outside. So dx over dt can be even further written as, you pull omega outside, you get b1 cos omega t minus b2 sine omega t. That's right. We got what is dx over dt. Let us try to find the acceleration now. Let us try to find d squared x over dt square. Well, in exactly the same manner, you will be pulling omega outside. So definitely you will be getting omega square. And the differentiation of cos is minus. So you will be getting minus on both sides. So you can also pull minus sign outside. So you'll be getting b1 sine omega t plus b2 cos omega t. So I have taken the minus sign outside, and I have also taken the omega outside. So that is d square x by dt square for you. Now we have x of t, we have dx by dt, we have d squared x by dt square. So that is what is demanded in the governing differential equation. Maybe I can say you need to substitute d squared x by dt square, dx by dt, and x in this particular governing differential equation. Let us substitute that. So the governing differential equation is m into d square x by dt square, and d square x by dt square is minus omega square into b1 sine omega t, b1 sine omega t plus b2 cos omega t, that's right, plus c into dx over dt. And what is dx over dt? It's omega into b1 cos omega t minus b2 sine omega t plus k into x. And you know what is x? It is b1 sine omega t plus b2 cos omega t. So this is the governing differential equation actually, except that I have substituted the values of d squared x by dt squared, dx by dt, x. So it is m into d squared x by dt squared plus c into dx by dt plus k into x is equal to the force that varies in a sinusoidal fashion with an amplitude f. That's right. Now in the next step, what I'm going to do is I'm going to take all the sine terms common, and I'm going to take all the cos terms common, pull sine terms common outside, right? So if I take all the sine terms common outside, I'll be getting minus b1 into m into omega square, because this is a one sine term, right? This is one sine term. Is there any other sine terms? Well, I have one more sine term here, b2, which is the coefficient of the sine term. And of course, I have c omega outside, so I have to write that also. So it's going to be minus b2 into c omega. So that's another sine term. And I have one more sine terms here, that is k into b1. So it's going to be plus k into b1. So these sine omega t. So sine omega t is taken common outside for all these terms. And I'm going to take all the cos terms common outside. So I'll be getting, see, b2 into these terms again. So it's going to be b2 minus b2 into m into omega square into cos omega t. There is a cos term here. So it's going to be plus b1 into c into omega. Any other cos terms? Yeah, well, there is a cos term here. b2, of course, I have to multiply by k. So it's going to be plus b2 into k into cos omega t. And that is equal to the sinusoidal force, f into sine omega t. That's right. I'll just do one more step here. So here we go. So let me do one more step. That is, maybe I can take b1 common outside for these two terms. If I do that, I'll be getting k minus m into omega square into b1. b1 is taken common outside, minus b2 into c into omega into sine omega t. That's right. In exactly the same fashion, can I do something over here? Well, what I can do is I can take b2 common outside. I'll be getting k minus m into omega square into b2 plus c into omega into b1, and that into cos omega t is equal to f into sine omega t. That's right, sine omega t. All right. Now you compare the left hand side and the right hand side. Okay, the right hand side has got f sine omega t, and you can see I can add one more term to the right hand side, plus 0 cos omega t. Well, if I do that, I'm not going to do any damage to the equations, because 0 into anything is going to be 0. Just by comparison, I can say the coefficient of sine omega t on the right hand side is f. The coefficient of sine omega t on the left hand side is these terms. I can equate them. Well, let me do that. So I'll be getting k minus m into omega square into B1 minus B2 into C into omega is equal to F. So that can be my first equation. I'm just comparing the coefficient of the sine terms on the left side and the right side. I can do this. In exactly the same manner, compare the coefficient of this cos term on the right hand side, it's 0, and compare the coefficient of the cos term on the left hand side, it's going to be k minus m into omega square into B2 plus C into omega into B1 is equal to 0. So this gives our second equation. Now all we have to do is solve 1 and 2. That's it. Solve 1 and 2 and you are almost there. So in order to solve 1 and 2, what I will do is I'll find B2 first, which is easy from this equation. I can easily find the value of B2. And I'm going to substitute the value of B2 in equation 1 and simplify. So what is B2? It's going to be minus C into omega into B1 divided by K minus M into omega square. Well, I have the value of B2 in terms of B1, and let me substitute that over here to get the value of B1. All right. So if I do that, let me do that in the next page. It is the first equation is K minus M into omega square, K minus M into omega square into B1. Am I right? That's right. Minus B2. So minus into minus is plus. So plus B2 is C omega. So that becomes plus C square omega square into B1 divided by C square omega square into B1 divided by K minus M into omega squared. K minus M into omega squared. K minus M into omega square. K minus M into omega squared. That's right. Then that is equal to F. That is equal to F. I can take LCM. So if I take the LCM, I bring this term here. It's K minus M into omega square, the whole square into B1 plus C square omega square divided by K minus M into omega square into B1 is equal to F. I can find the value of B1. So please tell me what is B1. It's very simple. It's F into K minus M into omega square divided by K minus M into omega square, the whole square, plus C square omega square. That's the value of B1. All right. Now, in the next step, I'm going to take this value of B1 and substitute it in this equation. Maybe call this a star equation, and I'm going to get the value of B2. All right. If I take this and substitute, I'm going to get the value of B2. So B2 is equal to, so you see here, K minus M into omega squared is in the denominator, that K minus M into omega squared is in the numerator, so we can cancel them. So it becomes minus C omega, F C minus F into C omega, K minus divided by, right, K minus M into omega square, the whole square, plus C square omega square. So that's the value of B2. So I have got the value of B1, which is F into K minus M into omega square divided by K minus M into omega square, the whole square, plus C square omega square. And I've got the value of B2, which is minus F into C into omega divided by K minus M into omega square, the whole square, plus omega square C square. Now all I have to do is substitute the value of B1 and B2 in this assumed solution. That's it. So the solution for the forced vibration, which is particular integral, is B1 sine omega t. Am I right? Yeah, that's right. B1 sine omega t, which is f into k minus m into omega square. F into k minus m into omega square divided by k minus m into omega square the whole square plus omega square c square. This is b1 into sine omega t plus b2 into cos omega t. b2 value is minus f into omega c divided by k minus m into omega square the whole square plus omega square c square into cos omega t. That is the solution. Now, can we take the common terms outside so that the solution can look even more elegant? Well, f is common, we can pull that outside, and k minus m into omega square the whole square plus omega square c square, that is also common, we can pull that outside. You will be left out with k minus m into omega square into sine omega t, all right, minus omega c into cos omega t. That's it. Now, just one last steps, couple of last steps. You see, this term I'm going to call this as, it's an assumption, capital X cos phi, and this term I'm going to call this term as capital X sin phi. Now you may ask me this question, can I really do that? Well, you can do that because k is just a number, stiffness is just a number, mass is just a number, omega is just a number. You are going to end up with a number, and any number, let it be 5 or 13 or 16, whatever it be, any number can be written as a product of cos some angle into x, some number, product of two numbers, that's it. Similarly, this is going to be a number, omega into c on the right hand side is just going to be a number. It can be written as x into sine phi. It's just written as a product of sine of some particular angle into a particular number. It's possible, right? Of course, these two numbers are related because what is common in these two numbers? Well, capital X. And it's easy to find capital X. All you have to do is square these two terms. So what happens is x square cos squared phi and add them plus x square sine square phi. So what do you get if you add these two numbers? Well, let us simplify this. If you're just going to add these two, then what you are actually going to get here is you can take x squared common outside, and that is going to be 1. That is just going to be 1 because cos squared psi plus sine squared phi is just going to be 1. That's right. And if you just do this on the right hand side, what is that you are going to get? You are going to get, you see, what is that? X squared cos squared psi, which means if you are squaring these terms, you are going to get k minus m into omega square the whole square, and if you are squaring these terms, this term, you are going to get omega square c squared. That's right. So squaring these two numbers, so you can get the value of x. It's simply root of k minus m into omega square the whole square plus omega square into c square. Well, this is one side, but keep this at the back of your mind. It will be very useful. But for now, let us replace the solution by cos phi term and sin phi term. So what happens, let us keep this. Let us continue the discussion. So x of t is going to be equal to capital F divided by c square omega square plus k minus m into omega square, the whole square. It is now, this time it's going to be x cos phi into sine omega t minus capital X sine phi into cos omega t. Now this is of the form cos, you can pull capital X common outside. So if you're pulling capital X common outside, well, you will be getting x of t is equal to f into, we just got the value of capital X, which is root of c squared omega squared plus k minus m into omega squared. In the denominator, that can be c squared omega squared plus k minus m into omega squared, the whole square can be written as root of c squared omega square plus k minus m into omega square, the whole square, into root of, that's right, c square omega square plus k minus m into omega square, the whole square. So root a into root a is just a, so you're going to get this expression back. If you're pulling this x term common outside, we just know what is x. It's a root of k minus m into omega square, the whole square, plus c square omega square. That's right. So if you look very carefully at these two, you can then inside you will be getting cos phi sine omega t minus sine phi cos omega t. This is of the form sine a cos b minus cos a sine b, so that can nicely be written as sine omega t minus phi. So if you just expand this by sine a minus b, the formula, it's sine a cos b minus cos a sine b. Now we can cancel these two, right? So the final solution to the particular integral, which is the force vibration solution, is f divided by root of c square omega square plus k minus m into omega square, the whole square, into sine omega t minus phi. So this is the solution to the particular integral. You can just add it with the free vibration solution to get the general solution, but this is the solution for the forced vibration system. Well, you can also find out what is this phi, right? You can easily find out what is this phi. So think about it. How do you find the value of phi? It's very simple. All you have to do is capital X sine phi divided by capital X cos phi, which is equal to omega c divided by k minus m into omega square. So that is tan phi. So tan phi is equal to omega c divided by k minus m into omega square. So you can easily find what is phi, which is tan inverse of this term. So that is the phase angle. So you can easily get the value of phi. So you got all the ingredients that you know what is phi, you know what is the force that is acting, you know the damping coefficient, the speed at which it is, the mass is spinning, the frequency, the forcing frequency that you know, the stiffness of the spring, mass, everything is known. You just have to, you can just feed it in in MATLAB or in Python, and you can code it up and you can simulate and see the results for different magnitudes of forces, damping coefficients, and phase angle. Thank you all for your patience. Thank you so much.